This is section 4.4. This is the second fundamental, I don't know why I keep trying to put that T there, fundamental theorem of calculus. Okay, so there we go. Second fundamental theorem of calculus. Now, let's just look at, suppose I want to do an integral, say, from 0 to pi of cosine of x dx. Okay, and I could look up what that is. I did something on Desmos here where, I wanted to maybe be able to change that. And so, what did I say? Pi. So, oops, equals. And then pi. Okay, and, I get 0. Okay, so this definite integral of cosine from 0 to pi is 0. And I have a point here, AF, that shows the A value of pi and the F value here of 0. And, well, I could go in here and do divided by 2, so I could do pi divided by 2. And, I changed it there. So I can get all sorts of different values by just putting an A there and changing A here. Now I can do a slider with that. I think I probably have to go to there. Well, maybe even just get rid of it. Click up in here, and well, it's sort of happy with me there, but I don't know. Let's try A, and then equals 1. See if it gives me a, yeah, there it gave me a slider. And we'll just go down here, and it defaults between -10 and 10, and I can grab that. And so there, you see, as I move that slider, we see the value moving around. Okay, so you see, A here could be thought of as a variable, and the X is just a dummy thing to tell me how to integrate or how to get that definite integral. But the real thing that's changing is maybe A. Okay, so now to do that a little better, I need to actually switch some things here because Desmos just doesn't like it. So for instance, notice if I go in here and I try to say f of A. Well, actually, this might work. Let me try it. F of A. Like that. Now, it doesn't like it right now because I've got a slider, but let me get rid of that slider. And there we go. Yeah, it worked just fine. So, and we'll get rid of that point. But you see, I've made this into a function where A is a variable, and now it's plotting f of A as a function of A along here. And look at it. Notice at 0 you get 0, at pi you get 0, at 2 pi you get 0, at minus pi you get 0. And so this looks a lot like the sine function. Well, is it? Okay, functions, sine, and x, and close that. And there we go. Green on top of the blue, they are the same function. Okay, and what the heck's the antiderivative of the cosine? Oh, the sine. So you see, this is really just doing an antiderivative here. Now, you know, it's one of the antiderivatives. It's sine plus a constant, but because we started here at 0, when a is 0, this evaluates to 0, just like sine of 0 evaluates to 0. Now, in your textbook for the second fundamental theorem, what they do is they'll put an x in here. So we'll get rid of that. We'll make that an x. We'll make this one an x up here. Okay, but notice it doesn't like that. So Desmos is pointing out that this is bad to do something like this, to say cosine of x dx and have an x up there. It doesn't make sense. You know, I just need a dummy variable down here. Now in the textbook they use a t. I would not use a t in Desmos. I would use any letters other than t, x, or r. And so here we'll get another s. And so as long as I get these things to match up with the s and the ds, you know, it does just fine. And there now I have that function. That's the sine of x. But you see, we can take the derivative of this function. Oh, why did I get rid of that? Don't know. I can do f prime. I need this up there. F prime of x. And we've got a few things here, right? That, well, they're both blue, but the highlighted one is the derivative. And notice that looks a lot like the cosine. Well, okay, remember this, because this is really just doing the antiderivative of the cosine, this is sine. And so then when I take the derivative, I get the cosine back. Okay, so what we're seeing right here is then in this second fundamental theorem of calculus, if I you know, so I'm going to forget about this, and I'm going to say, oh, well, I've got f of x is the integral from 0 to x of cosine of s ds. You can use a t when you're doing stuff like this. Again, Desmos is just not the best idea. Now, and in this particular case, we get sine of x. Well, so notice what happens is f prime of x is just equal to that thing with an x in it. So cosine of x. Okay, that x just comes down there and we get cosine of x. So that, and that's actually going to be true no matter what this constant is. So if we change that constant, we'll get sine of x, but plus some arbitrary constant. Something, you know, right? Something sort of funky will happen there. And we can look at that. Let's go back to Desmos. And let's change that 0. Okay, backspace. I don't know. Let's change it to pi divided by 4. And notice what happens, right? There's our function. Kind of hard to see it there. Here's our function, right? It's dropped down on the axis here with that pi over 4. But notice the derivative is still the cosine function. Okay, so what happens is as I change the constant down here, I'll come back here, as I change that constant down here, you know, it's just going to change this, the value of c. Okay, and we can kind of see that with using our antiderivatives, and just the usual idea is if I say, this is f of x, and that's the definite integral from 0 to x of cosine of s ds. Well, just following the rules of what this is, I would take the antiderivative of cosine, which is the sine, and of s, and I would evaluate at 0 and x. And so I get sine of x minus sine of 0. But sine of 0 is just 0, so I just get sine of x. Now, if I define f of x as the integral from pi over 4 to x of cosine of s ds, again, just from evaluating that as an antiderivative, so sine of s, and then putting in my limits here of x and pi over 4, I get sine of x minus sine of pi over 4. Okay, well, sine of pi over 4 is square root of 2 over 2, and so I get minus square root of 2 over 2, or about, what the heck is that? 1 over the square root of 2, or about 0.707, I think. So there's my function, and we can see how that works. But now notice, right, if I take the derivative, so f prime of x, well, that's just the derivative of the sine of x, and whether or not I have that minus square root of 2 over 2 or 0 or whatever, it's just a constant, and I get cosine of x. So I just get whatever's in there, no matter what that constant happens to be. Okay, so our second fundamental theorem of calculus is that, I can define a function f of x this way using a definite integral, and I can use 0 or whatever in the textbook. They use 0, but really it could be, well, I guess in their definition they use an a, and so x, and then f prime of, they use a t, dt. But then notice that f prime of x is, well, it's whatever's in there, it's f prime of x. Okay, you put that x in there. Now you can make that look a little more interesting by saying f prime of x is f of x, like that, and then when you write this, you could write f of big F of x there, uppercase f of x, integral from a to x of little f of t dt, like that. And then when you say f prime of x, you'd say little f of x, like that. Okay, from that. So that looks a little more interesting, but that's all that's happening, is you're saying, hey, right, this basically, when you do this antiderivative stuff here with the integral, well, that's just it. You're doing an antiderivative. So when you take the derivative, you get back to where you started. And that is the idea of the fundamental, second fundamental theorem of calculus.